Okay, so before we get going with the function that generates the connected diagrams, I just want to stress that we have studied three different properties of graphs. So we've got three different ideas, and they're important. So I just want to spend a little bit of time making sure that we've really understood them. So the first idea is whether a graph is connected. Let's put a big C there for connected. Whether it's disconnected, let's put a big D there for disconnected, or whether it's vacuum. Put a big V there for vacuum, okay? And let's just make sure that we understand what these mean. Let's study, study four correlators in the old normalization. So if we look at phi 4, what does this look like? Well, we've got that plus, we're not going to draw all of the diagrams, but let's just draw a few of them. So we've got diagrams that look like that. Then we've got diagrams that look like this. And there are more like that. We've got diagrams that look like this. And a diagram that looks like this. And then if we were going to second order, we could have stuff like that. We could have stuff like that. And we could have stuff like that. So this first line here is order 1, g to the naught. These lines over here are order g. These lines over here are order g squared. I'm not drawing all diagrams, and so it would continue. Okay, now I want you to label all of the diagrams that are connected. So pause the video and label what's connected, then put it back on again, and let's do it together. Okay, for the connected diagrams, well, this one is certainly connected, and this one is connected. Good. Okay. Now I want you to do exactly the same thing, but label all of the diagrams that are disconnected. So pause the video and label it. Okay, did you do it? Let's check. This is disconnected. This is disconnected. This is disconnected. 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 So if the diagram is connected, it's all one piece. Everything's connected. If you imagine this diagram as some structure, if you are an ant on one piece of the structure, you could walk everywhere on the diagram. For the disconnected diagrams, walking on the piece of the structure that you're on does not allow you to walk everywhere. Finally, let's label what is vacuum, okay? So again, pause the video and check what's vacuum. So pause the video and do it. Okay, did you do it? Good. Let's tease out the vacuum diagrams. So this one is a vacuum diagram. That's a vacuum diagram, and that's a vacuum diagram. So take a look, for example. So I'm going to just discuss some diagrams. Look at the diagram that I've underlined in gold here, okay? So the first particle, the particle on the left, just propagates along and nothing happens to it. The particle on the right interacts with the vacuum, but the particle is interacting with the vacuum. That's not a diagram where the vacuum is doing something on its own. Look in contrast to this diagram that I've just underlined in gold now. Our first particle propagates along and does nothing. Our second particle propagates along and does nothing. And then that figure of 8 diagram on its side, or the infinity sign, that's the vacuum doing something on its own and not interacting with our particle. So the top gold diagram is disconnected but not vacuum. The bottom gold diagram is disconnected and it's vacuum. Okay, so we've now labeled everything as connected or disconnected, and everything had to be either connected or disconnected. And we've gone further and we've picked out the diagrams that were vacuum diagrams. Okay, now notice something. So there's a rule here, and I think it's good to state this rule explicitly because sometimes there is a little bit of confusion here. So every vacuum diagram is disconnected. Okay, look at our labeling. Every vacuum diagram is disconnected. We've got 3 vacuum diagrams. They're all disconnected. And that's always true. Every vacuum diagram is disconnected. Let's say not every disconnected diagram is a vacuum diagram. Okay, so every vacuum diagram is disconnected, but not every disconnected diagram is a vacuum diagram. So if you've understood the labeling and you've understood these last 2 statements that we've made, then you've got the point. Then you really have absorbed these concepts of connected, disconnected, or vacuum. And remember, it's the connected diagrams that somehow are telling us about interactions. So the connected diagrams are inherently interesting. So the question that we want to ask ourselves now is, how do we generate the connected diagrams? Okay, so that's the question we want to ask now. And I'm going to tell you the answer. So introduce a new function, w of j. And w of j, by definition, is the log of z of j. Then, if you wanted to calculate phi to the n, the connected piece, well, this would be equal to n derivatives of w of j with respect to j evaluated at j is equal to 0. So what is this telling you? W of j generates the connected correlators. W of j generates the connected correlators. Now, you could give a combinatorial proof of this that is not very instructive or interesting, or at least not to me. So we're not going to bother to do that. What we are going to do, though, is we're going to check this formula in the black box. And we know how to work out phi to the n connected. So we can work out some correlation functions, pick up the connected diagrams. We've worked out what z of j is. We can calculate the log of z of j, calculate derivatives, and check the formula in the black box. So that's what I want to do, and we're going to spend a little bit of time doing that. But before we do that, let me ask you something, or point something out, okay? This is something that maybe you are wondering about. We had 2 objects that generated the Feynman diagrams. We had z of j and z hat of j. And they only differed in a normalization. Z of j would generate all Feynman diagrams, including vacuum Feynman diagrams. Z hat of j will generate all Feynman diagrams that are not vacuum diagrams. So Z hat of j will not include vacuum diagrams. Z of j does. What if we decided to define W hat of j, which is equal to the log of z hat of j? How do the Feynman diagrams generated using W hat agree or disagree with those generated using W? Well, we know what z hat is. Z hat of j is z of j over z of naught. And manipulating logs, is a triviality, especially for you guys. So you know that this is just the log z of j minus the log z of naught. Okay, now let's try to see what would the correlators generated using w hat look like. So we take n derivatives of w hat of j, djn. Actually, you know what? I want to rewrite this formula just above in a slightly different way. Good. We can write this as this is equal to w of j minus log z of naught, okay? So let's take these n derivatives. Well, obviously we need to take n derivatives of w of j, dj to the n, and then minus, we need to take n derivatives of the log of z of naught, dj to the n. But the log of z of naught is a constant because we've set j equal to 0. And if you differentiate a constant with respect to j, you're just going to get 0. So this term vanishes. So what you learn is that generating correlators with w of j gives exactly the same answer as generating correlators with w hat of j. And that makes sense because the only difference between z of j and z hat of j is one includes the vacuum diagrams and the other doesn't, but vacuum diagrams are never connected. So if you're only picking up the connected diagrams, who cares if the vacuum diagrams are there or not? The connected pieces never involve the vacuum diagrams. Great, we'll continue in a moment.